Alright, here we go. We're talking about those famous Sig Figs that I've talked to you about. These are those important numbers. I told you, 1 divided by 3, it might be 0.3, it might be 0.33, it might be 0.333. It'll never be 0.3 forever. So what are Sig Figs? Sig Figs are going to be those reliable numbers in a measurement. If you are making a measurement or reading a device that records a measurement, Sig Fig rules are being followed. If you're making a measurement, you will have to follow those Sig Fig rules. Here's the hint. You record everything you know, and then you add one estimated position. If you're reading a digital device, the last number displayed is the estimated position. So when you do some labs for me back there where you're using the electronic balances, those devices are following Sig Figs. If you're using something that's manual, like reading a graduated cylinder or reading a meter stick or ruler, you will be the one that has to apply those Sig Fig rules. Every experimental measurement has a degree of uncertainty. We can only read so much of it, and then the rest of it is kind of an estimate. The volume at the right. See, here's the thing. I can definitely read the tens position. There's 10, there's 20. If we keep going on up, there's 30, 40, and so forth. So I know that it is definitely 10, but I know that it's less than 20. The other thing is, when I go ahead and look a little bit closer, you can see that it is divided out into the individual one spot. So 11, 12, 13, 14, 15, 16, 17. So again, I look in a little bit closer here. We know that it's 17 point something. Again, like I said, that one's position is known. But after that, when you look here at 17 and 18, it is not divided out anymore. So the thing is, you will have to give me an estimated position. So if I'm looking here, somebody might say it's 0.4. Somebody might say it's 0.5. Somebody else say it's 0.6. I don't think anyone would come out and say, hey, it's 0.9 or it's 0.0. Again, it's somewhere around that middle. So if I were guessing it, I would probably say about 17.5 milliliters. Remember what I said, read everything you know and add one estimated position. So we could definitely say we know it is at least 17, less than 18, and then I'm estimating that tenths position. Again, if I go ahead and I look at this ruler here, I know it is definitely 1, but I know it's less than 2. Okay? It's divided out even further, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. Okay? And then we know that it's a little bit less than 0.7. So again, we know it's between 1.6 and 1.7. But when we look here, there are no other divisions between the 0.6 and the 0.7. So the thing is, we have to make an estimate between 0.6 and 0.7. Again, if I were looking, I'd probably say it's definitely over the 0.5. But again, a little bit more, so again, probably estimating 1.67. That last digit, 7, that was our guess. That was our estimated position. So again, the 1 is known. The 0.6 is known. That 7 is going to be our estimated position. What is the length of the wooden stick? Again, I've got 4.5. I've got 4.54. I've got 4.547. Well, let's go ahead and look here. We know it's definitely 4. We know it's definitely 0.5. 1 is out because we don't have an estimated position after that. Again, I know that it's less than 0.6. I now have to look and say to myself, there are no further divisions between that 0.5 and 0.6, so I'm going to estimate that next position. So our correct answer is going to be 4.54. If I go ahead and I look at this pencil, and again, we go ahead and use this back side here for the pencil. Again, I know it's more than 7. I know that it is possibly 8. Okay, maybe it's a little less than, but I'm going to say it's 8 right on. Okay, so if I say that it's 8 right on, thing is, I'm going to go ahead and write down my 8. I'm going to draw my decimal there. Now, again, we can see that it's divided out 0.1, 0.2, 0.1, 0.2, and so forth. But the thing is, I think it's right on 8. So I'm going to go ahead and draw a 0 in there. Now again, when you look here, there are no further divisions, and if I say that I think it's exactly right on that line, I'm going to go ahead and draw another 0 in there. So the correct measurement on this one is 8 12.00 centimeters. If we go ahead and start looking at some measured numbers, do you see why measured numbers have error? You have to make that guess. But again, that's what makes science unique. That's what tells the reliability of an experiment. Again, the more numbers a scientist is able to give, the more precise or the better their equipment ends up being or ends up telling us. All but one of the significant figures are known with certainty. That last significant figure is only the best possible estimate. And again, as I say, read everything you know and add one estimated position. To indicate the precision of a measurement, the value recorded should use all of the digits known with certainty and then that one estimated position. Like I said, if you're reading an electronic instrument, it already does Sig Figs for you. If you were to go back and record 12.15 grams, that last 5, okay, or that last number, 12.15, that 5 is going to be estimated. It knows that it's at least 12 and it knows that it's for sure 12.1, but that 5 is going to be what's estimated. An exact number is obtained when you count objects. And when you count things, that is a definite number. The other thing that is definite is defined relationships. These will have an infinite number of Sig Figs also. For example, when I say 2 soccer balls, you can see one soccer ball, you can see the second soccer ball. That's a definite. Those are infinite Sig Figs. If somebody brought in 4 pizzas, again, we can count each and every one of those pizzas. That's a definite. And definite things have infinite number of Sig Figs. The other thing, 1 foot is 12 inches. That's an exact. 1 meter is 100 centimeters. Those are exact. So those have infinite Sig Figs also. Anytime you're using those SI prefixes, 1 kilometer is equal to 1 times 10 to the 6th millimeters. That's an exact. Those have infinite Sig Figs. Now, when I say it's 12 miles from here to Deschler, that's somebody's estimate. Somebody measured that out. But again, that is an estimate number. That is not an exact number. Things that you can count. When I say that there are 10 students, those are exact students. I mean, we don't have 3/8 of a student. We know that each individual is one whole student, and those are infinite. And then, like I said, 1 foot, 12 inches, 1 hour, 60 minutes. Those are exact, and those are infinite Sig Figs. For instance, 1 foot is not 12.000001 inches. No, it's exactly 12 inches. And those exact things have infinite Sig Figs. Now there's 5 Sig Fig rules. Okay? So it says when reading a measured value, all non-zero digits should be counted as significant. For example, that number 842 has 3 Sig Figs. What I'm saying is all numbers 1 through 9 are significant. Okay, all numbers 1 through 9 are significant. So when you look at this number 842, the 8, the 4, and the 2, those are all non-zero numbers. So each one of them counts. So we say that it has 3 Sig Figs. There is a set of rules for determining if a 0 in a measurement is significant or not. And that's what really the rest of the rules do, is they deal with 0 numbers. Zeros that are in the middle. I call this one my sandwich rule. Okay. Again, we're going to use rule number 1 where non-zero numbers are significant. But if a 0 is scrunched in between, it will count also. So it says zeros in the middle of a number are like any other digit. They are always significant. So this number, 94.072, if we go back to rule 1, the 9, the 4, the 7, and the 2 are significant. Because that 0 is stuck in the middle, we know that it is now going to count also because of rule 2. So this number, 94.072, will have a grand total of 5 significant figures. Zeros at the beginning, those numbers that are used just as placeholders, those numbers that act just as placeholders, those are not going to count. Okay, those will not count as Sig Figs. The thing is, I need the 8 in the hundredths position. And the only way I can place the 8 in the hundredths position is by having that 0 out in front. So these front zeros will not count as Sig Figs. So what I do is I just go ahead and I cross them out and I say, well, the 8, the 3, and the 4, those count. Okay? These down here, these front 2 zeros, they're not going to count. The 2, the 9, and the 7, that's rule 1, non-zero numbers. Those are significant. This 0 here, that's rule 2. That's my sandwich rule. So this number here has 4 significant figures. Rule 3 is telling you these front two zeros that are used just as placeholders are not going to count as sig figs. Rule 4, final zeros. Final zeros are also going to be significant. So it says here, zeros at the end of a number and after the decimal point are significant. It says it is assumed that those zeros would not be shown unless they were significant. So the number 138.200, that has 6 significant figures. 1, 3, 8, and 2, that's rule number 1. These are ending zeros. And if they're ending zeros or final zeros, they are going to count. If the value were known to only have 4 sig figs, we wouldn't have to place those zeros on there. Okay, we could only record 138.2. Notice the difference. This is my estimated position. This number right here is saying we know the 1, the 3, the 8, the 2, the 0, and this is my estimate. 6 sig figs is a lot more reliable than 4 sig figs because down here the 1, the 3, and the 8 are known. That one is my estimated position. And then rule number 5, it says zeros at the end of a number and before an implied decimal point, they may or may not be significant. We cannot tell whether they are there or not, and they act only to locate an unwritten but implied decimal number. Here's what I'm basically saying. If I say the number 20, and over here I put the number 20, but I put a decimal right there, okay? The number 20 without the decimal there, that only has 1 sig fig. If I come over here and you see a decimal, that decimal means count the 0. So the number 20 here will have 2 significant figures. No decimal, don't count the zeros. Decimal, count the zeros. So if I were to give you the number 1,000, and I were to not put the decimal there, this number right here has a grand total of 1 sig fig. Okay, that is the only sig fig right there. But the minute that I put that decimal there, okay, the minute I put the decimal, that now says that that 0, and that 0 count. Okay, when numbers are expressed in scientific notation, it doesn't matter if they're non-zero numbers or they're 0 numbers. What you do with scientific notation is count everything in the M. The 6, the 7, the 0, the 0. When you look at that number right there, there's 4 numbers. All of them are significant. Everything written in the M portion of scientific notation is going to count as being significant. Here's what I want you to do. I want you to go through and I want you to write down in your notes. I want you to write down how many each of these numbers is going to have for sig figs. So I've got 2, 4, 6, 7 examples here. Tell me how many sig figs are in each of these numbers. Okay, rounding off numbers. A lot of times when you do calculations on a calculator, the answer is displayed with a lot more significant figures than are really justified. Again, that number 1 divided by 3, your calculator screen is going to fill up with 3s. Okay, how many of those 3s can we count? How do you decide how many digits to keep? Well, again, there's going to be rules for addition, subtraction, multiplication, and division. When you do multiplication or division, what you do is your answer cannot have more sig figs than either of the original numbers. Now you might be saying, what does that mean? Here's what I'm saying. Make your answer have as many sig figs as the number that you are multiplying or dividing has the least. So when I look at this example here, 278, that has 3 sig figs. 11.70, that has 4 sig figs. 3 is less than 4, so my final answer can only have 3 sig figs. When you are multiplying and dividing, your answer can only have as many sig figs as the number over here with the least number of sig figs. When you add or subtract, the answer cannot have more digits after the decimal point than either of the original numbers. What I'm saying there is use your last complete column. So when I look at this number, the number's 3.18. Notice this is in the hundredths position. When I look at this number down here, tenths, hundredths, thousandths, 10,000ths, 100,000ths, my final answer has to go to the one that is the least precise or the last complete column. This has a hundredths column, that has a hundredths column. I have to make my answer correspond to the hundredths column. This one has a thousandths position, but guess what? This one up here doesn't have a thousandths position. So again, I can't use that number. This one only has the hundredths position, so my final answer can only be in the hundredths position. Here's what I want you to do. I've multiplied all of these out or divided all of these out. You can see the numbers. When I take 32.27 times 1.54, this is what my calculator gave me. I want you to give me the correct Sig Fig answer. Division, give me the correct Sig Fig answer. Do that for all 5. Okay, again, I've done some addition and subtraction. I've given you the answers right here. Again, you can see that. What I want you doing is writing down what the final answer would end up being. A few more addition and subtraction. Again, notice these are going left to right. If you need them going up and down or vertically, go ahead and put them vertically. And the last one here, what I have is I have some mixed operations. I've got some addition, I've got some multiplication, and I've got some addition again. So what I need you doing is, again, notice here, you always do your multiplication first, and then go ahead and do your addition, and go ahead and record your final answer. Same thing down here. Notice we got to do the parentheses first, get your sig figs, multiply, and then give me a correct final answer.